Yes, they're mostly graded. I'll post the grades and distribute the key as soon as I give the last makeup, which should happen Wednesday before class, so you'll have them Wednesday at class. Meanwhile, I want to take another moment to look more precisely at continuity and some of its effects. We had the intermediate value theorem, which told me that for a continuous function, it takes on all the values between f of a and f of b when I have a continuous function on a closed interval. Differentiability is stronger than continuity. Every differentiable function is automatically continuous. So I should be able to get a stronger, similar result. And there are two versions of this. It starts my friend Roll. I have a 3 or 4 page paper that talks about the history and development of this idea. As a matter of fact, there's an entire website on teaching with historical sources. We can actually read Roll's original work. And the consequences that Cauchy and others came up with that will be the mean value theorem. But they all start geometrically from a fairly similar place. Let's consider a function. And I want this function to be continuous on some interval. I want it to be differentiable. I don't care about the very ends, but I want it to be differentiable everywhere else. And I want the endpoints to have the same value. Now, just as we did for the mean value theorem, for the intermediate value theorem, I think this is best done with a picture. I want you to draw any graph that satisfies these 3 conditions. No matter what picture you draw, you've got f of a, you've got f of b, they're the same height. You're going to play connect the dots. Somewhere in between, you must have a horizontal tangent line. I don't care what picture you drew. Angela, when you started at f of a, did your function go straight across, up, or down? Okay? So if I start at f of a and I go up, what has to happen somewhere? I didn't quite hear you. I have to come back down to here at some point, right? And it's continuous and differentiable. So there can't be a corner or a cusp or a vertical tangent line. And there has to be a return to that same height. I don't care what the graph looks like in between. Somewhere, I've got an extreme value. And according to what we did last week, if I have an extreme value and the derivative exists there, and condition 2 says the derivative exists everywhere between a and b, then the derivative must be 0 at that extreme. Gage, what if I'd started out going down instead of up? Somebody help me out. What if I'd started out going down instead of coming up? I'm going to have a minimum somewhere in between, right? Doesn't matter what the graph looks like, somewhere between A and B. If I started out going down, I've got to come back up at some point. I could go up and down multiple times. That's not prohibited. There's some C, there could be more than one. Right? It absolutely can be a straight line. If I'd done completely horizontal, then every value between A and B would work, wouldn't it? Well, if I could draw straight, then yes. So I have lots of options that give me places where my function must have an extreme. And according to Fermat from last week, if I have an extreme, I have to have a horizontal tangent line. Now, I will agree with you, this is a fairly theoretical and abstract idea. What good is it? One of the big things that algebra was stuck on was solving equations. And at the time Rolle is working historically in mathematics, there's a lot of argument over finding the roots of an equation. In the late 1500s, Cardano and Tartaglia came up with formulas for solving cubic equations, and people were pissed off. More so than they had been about the quadratic formula, because the quadratic formula is what gave us imaginary numbers, square roots of negatives, and people went, what the fuck are you smoking? Because that doesn't make any sense at all. But Cardano and Tartaglia showed not only do these things still work, they continue to work for higher powers. When we can find those roots, finding them isn't exactly trivial. So something that was often needed was, well, how many roots am I looking for? How many answers does this problem have before I start trying to figure out what the hell they are? Like with Newton's method or something like that, finding the roots of an equation. How many should I be looking for? It's a cubic equation. This cubic equation could have as many as 3 different roots. How the hell can I show it only has 1? How do I show it has at least 1? It's polynomial. Polynomials satisfy those first 2 properties, right? They're continuous everywhere, they're differentiable everywhere. So even before I want to show that it has exactly 1 root, I should show it has at least 1 root. And I'm going to cheat and jump all the way back to my definition of continuity and the intermediate value theorem. How can I use the intermediate value theorem to show that this has a root? Has nothing to do with roots, unfortunately. Because at this point, I don't know what interval I'm looking for extrema on. So looking for extrema at this point actually does me no good. A root is where we cross the x-axis. How does the intermediate value theorem help me find that? Turn back in your textbooks. Find me the intermediate value theorem. Chapter 2, section 5-ish, where do we discuss continuity? I'm sorry? Sure, read it to me.
F is continuous for some interval f of a is not equal to f, then for any value n between f of a and f, there is x value where x equals c, with f of c equal to n.
Ah. So if I know that there's a value down here and a value up here, we're going to hit every value in between. How can I use this to help find a root? A root is where the y value is 0. So if I find a place where the y value is below 0 and another place where the y value is above 0, then we have to cross somewhere in the middle. Whether we go from down to up or up to down doesn't matter, as long as I change sign somewhere. What's f of 0? That's the y-intercept of this graph. This is a cubic graph. I have to think all the way back to my algebra class where I talked about the rough shapes of polynomials. What's x squared look like? What's x cubed look like? One side goes down and one side goes up. So the left side should be going down and the right side should be going up. I'm at 1. Let's back up a bit. Pick an x value smaller than 0. Plug in -1. What do you get? Aha. We went from negative to positive. At -1, we were below the axis. At 0, we were above it. Somewhere between those two is a root. Let's give this x value a name. A. I don't know what this x value is. I just know it's between -1 and 0. I could narrow this interval. And I could say, all right, well, let's look between -1 and 0.5, -0.5, or between -0.5 and 0, see which half it's in. And then I could narrow it again, right? I could keep zooming in if I wanted to. But really, I don't care. I just care, hey, there's a root somewhere between these two numbers. Now, I have a root. My goal is to show we can't have another one. The claim at the top says exactly one real root. So here is an exercise in formal logical proof. Yeah. Remember geometry class, we had to prove stuff? I'm going to prove something here. Only rules I'm allowed to use. Rules of deductive logic and reasoning. This is a pain in the ass. I know. Curl your lips here. We'll get over it. I promise this isn't as crazy as you think. I'm going to make an assumption. Somewhere there is another root. If this thing has two roots, what has to happen between those two roots? Somewhere between the two, the slope will have to be 0. Because I'll replace f of a is 0 and f of b is 0. Somewhere in between, there'll have to be a horizontal tangent line. So put a big star here. Suppose we have a second root. X equals b with f of b equals 0. Now, I'm going to apologize in advance. In the statement of Rolle's theorem, we went from A to B. And that makes the assumption that B is to the right and A is to the left. It doesn't really matter in this case, whether it's A on the left and B on the right, or B on the left and A on the right. So I'm going to use the word between a lot instead of going from A to B. F of A is 0, f of B is 0. Everywhere between A and B, this function is continuous. Everywhere between A and B, this function has a derivative. by Rolle's theorem, there needs to be a value C between A and B where we have a horizontal tangent line. It's a polynomial, it's continuous. It's a polynomial, it's differentiable. Everywhere, not just between A and B. And we know that f of A equals f of B equals 0. So there exists some C value between A and B with f prime of C equals 0. If we have a second root, we have a horizontal tangent line somewhere. Yes, ma'am. That's what a root is, right? Where we cross the x-axis. So its y value is 0. I don't know what A and B are, but I know f of A is 0 and f of B is 0. I have a point where I know the tangent line has a slope of 0. Find it. Find C. I need f prime. You already wrote down the function. What's f prime? So if I plug in C, I should get 0. What's the value of C? Well, large numbers of curse words flow through my head. The conclusion we drew is not possible. I have reduced my assumption to a statement that is absurd. That doesn't make any sense. You said there was a number between A and B. Square root of negative 1/3 is not between anything. It's imaginary. It's off to the side somewhere. If this is impossible, then the assumption we made must be wrong. This idea, called reduction to the absurd or proof by contradiction, we've ended up with something that contradicts the assumption we made. The assumption must be wrong. What was our assumption? That there is a place where f of b is equal to 0. There's a different spot, a second root. No matter what number you try and pick, you'll never get another place where the output is 0. If there were such a place, we'd have a horizontal tangent line, and you can't do that with the function 3x squared plus 1. It's never going to be 0. Now, what does that mean for the graph of our function, our cubic equation? It goes through the x-axis between -1 and 0, goes through the y-axis at 1, and never goes back. It never turns around, because wherever it would turn around to come back down, that would be our extreme. And we don't have one. I can't look at every x value, can I? There are infinitely many of them. But what I've done in 1, 2, 3, 4, 6 sentences is rule them all out in one fell swoop. That's pretty damn powerful, if I do say so myself. Half of math is learning how to calculate, learning how to perform the calculations that are necessary to do other things. The other half of math is figuring out why they work that way. This is that part. I ruled out infinitely many other numbers in 6 sentences. Not bad for 15 minutes. Rolle's theorem allows me to think about extrema as long as I can think of the function as doubling back somehow, turning around. That's what our extremes are. Questions? Pierre Fermat saw Rolle's paper and said, that's a good idea. I think I can do better. Fermat said, I don't like the restriction Rolle put on requiring f of a to equal f of b. I don't like that. So let's throw that out. I'm going to get rid of the idea that f of a is equal to f of b and just work with the first two conditions. I have a function that's continuous everywhere on this interval, including the endpoints, and it's differentiable everywhere except maybe not the endpoints. I want to draw a conclusion here that is similar to what Rolle concluded. But I think, again, a picture is going to help us. So I want you to draw a graph. From A to B. We'll go ahead and do it again with A on the left and B on the right. Give me an f of A and an f of B. One of them is bigger or smaller than the other. Let's not work the case where they're equal, because that's Rolle's theorem. I already did that. But what if they're different? You want to go up, you want to go down. As you go from left to right, is f of a lower than f of b, or is f of a higher than f of b? Say again, higher. So if f of a is higher than f of b, my picture is going to look like this. Now, Fermat was one of the people who really exploited Descartes' idea of drawing the Cartesian plane, and Fermat was very happy to work with visual images. And so Fermat said, I want to ignore the axes for a minute. Let's turn the picture. Now, I promise I didn't turn the picture for the hell of it. If you ignore the axes, what do you notice about the heights of those two dots? They're the same. And that means that Rolle's theorem works there. Rolle's theorem would have me draw a line. The horizontal line between those two dots, right? And then I'm going to draw a graph from one point to the other. What do you know about that graph? By Rolle's theorem. That was the specific case. What's the general version of Rolle's theorem tell me? It says somewhere between those two dots, there'll be what? A minimum or a maximum with a horizontal tangent line. It might be that straight line, right? That would make every point. But let's draw the graph again. Do you want to go down first or up first? We went up first last time. Let's go down first this time. So I'm going to go down first, and then I'm going to come back up. I'm going to overshoot and come up and keep going down, right? And I know that there should be at least one spot, in my case, I've drawn it with two, where we have a horizontal tangent line. One of them is about here, and one of them is about here. That's what Rolle's theorem would tell me if I didn't have those stupid axes in the way, right? Well, fine. Let's turn the picture back. None of my lines are horizontal now, but they do all have something in common. They're parallel, which means the slope here is the same as the slope here, is the same as the slope here. Out of all of those, I know one of those slopes. The slope of this line. What is the slope of that line? I don't know what number it is. Change in y over change in x, right? But I know change in y, I know change in x. And what we've just found is that there are, in my case, two, but at least one point where the slope matches. The slope matches what? The slope here matches this one. But what's the slope here? What kind of a line is that? It's parallel. It's got a slope that's negative. In this case, if I'd drawn it going up, it would have a different slope. But that's a tangent line. Its slope is found using what? The derivative. At some point, this slope matches this slope. That's the conclusion Fermat came up with. Somewhere between A and B, there'll be some x value, call it C, whose slope is the average slope. This is the average rate of change, isn't it? It's another word for average. The mean value, son of a bitch. I happen to find two of them this time. In the picture I drew. Somewhere between x equals A and x equals B, there's a point where the instantaneous rate of change matches the average rate of change, matches the mean value of my slope. I drove here today. I live 26 miles from here. It took me 40 minutes. How fast was I going? On average. You own a calculator. You don't have to do this in your head. 26 miles in 40 minutes. $39 miles an hour on average. I didn't back out of my garage at 39 miles an hour. I sure as hell wasn't doing 39 miles an hour on the parkway. And I'm pretty sure I wasn't doing 39 miles an hour coming up the hill. But at some point between the time I started and the time I parked, my speed was exactly 39 miles an hour. My instantaneous rate of change had to match my average rate of change. You just told me my average rate of change is 39 miles an hour. There was an attempt in the state of Pennsylvania to use the turnpike ticket system to issue speeding tickets. I get on the parkway, I get on the turnpike here in Irwin. I go to Pittsburgh. It's 12 miles. You can tell me how long it takes me to get from point A to point B, right? If it took me 10 minutes to go 12 miles, how fast was I going? "12 miles in 10 minutes. 72 miles an hour. What's the speed limit on the parkway, on the turnpike? It sure as hell isn't 72. I should get a speeding ticket. Because somewhere in the realm of those 10 miles, I was doing 72 miles an hour. I was speeding. The calculus got laughed out of court as being too complicated for people to understand. No, it got too complicated to enforce because which county issues that ticket? Westmoreland County or Allegheny County? Where were you speeding? I don't know. Now, in order to use the mean value theorem, I need an interval from A to B. Let's see if we can find the particular point between 1 and 5 where the conclusion of the mean value theorem is satisfied. So I need two things. If my goal is to solve this equation, I need the derivative of my function, and I need the average rate of change. You can do this. Find the f of b minus f of a over b minus a, and find me f prime of x. If I plug in 5, I get 15 over 7. If I plug in 1, I get 3 over 3. But that's just 1, right? So it'd be 15 over 7 minus 1, which is the same as 8 over 7 over 4, which gives me 2 over 7. Trust me, it's easier to stay in fractions than it is to do this in decimals because sevenths are ugly. What's f prime of x? Quotient rule, absolutely. Now, I'm going to set this result equal to something and try and solve. That means it's probably easier to do all the algebra to simplify this derivative as far as I can take it. Derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. So that's 3x plus 6 minus 3x over x plus 2 all squared. Well, wait a minute, the 3x's cancel. I'm just left with 6. Great. In order for me to find the C value I want, I set f prime of C equal to my rate of change. Cross multiply, and I get 2 quantity C plus 2 squared equals 42. C plus 2 squared equals 21. So C plus 2 is plus or minus the square root of 21. Subtract 2. Negative 2 plus or minus root 21. I got two of them, right? Say it again. They need to be between 1 and 5. If I take negative 2 minus the square root of 21, I don't know what that is. I just know it's negative. I'm only looking between 1 and 5, so I can't use that one. Square root of 21. I have no idea what that number is. The square root of 16 is 4, and the square root of 25 is 5, so it's between 4 and 5 somewhere, right? You subtract 2, that'd make the number between 2 and 3, which is in the right section. Good. Ta-da! I can use the mean value theorem to say that my derivative is a limit on the way my function grows. I can use it to say, oh, well, my derivative is less than 3. If I go in a straight line, 3x goes up really fast. I've got to be less than that. I can picture a maximum a year down the line, a day down the line, an x value down the line. The mean value theorem, there's an example in the text, can be used as a bounding idea. There are two corollaries that follow from the mean value theorem that are really important to us in the long run. If I have a region, an interval where my derivative is 0, then my function must be a horizontal line there. And then I can say, oh, if I have two functions whose derivative is the same on some interval, then their difference is 0. F prime minus g prime will be 0. And that means that f minus g is a constant. I'm going to come back to that one and use it over and over and over. When I know something about a derivative, I can now know something about the function it came from. I will put all of this to more concrete use moving forward. This is today. This is Wednesday. Because the homework's due Thursday. Because we had another day with an exam, so it would be 3 days, right? There you go. I will see you all on Wednesday. Thank you.